So we're moving into talking about light in the electromagnetic spectrum. This still behaves as a wave, but light and anything within the electromagnetic spectrum is made up of something called photons. And the best way to describe photons is that they're tiny packets of energy, and they're going to make up the electromagnetic wave. They behave both as a wave and a particle, and they have oscillations that are both magnetic and electric. And so this is a case when we're looking at different ways to model things. The best way we can model it is saying, well, it's sort of a wave and it's sort of a particle, but really there's not much else that's going to behave like this. And so we do our best scientifically to model it as a wave, but also know that it has some particle tendencies that go along with it. It behaves as a wave in the way that it has a frequency and a wavelength that carries energy with it, but the difference is that this wave doesn't need a separate medium as other waves do. So we talked about sound, it needs something for it to travel through like air, but in this situation, the photon itself is the particle that carries it, and so it doesn't need something else. It's why you can see the sun, but you can't hear the sun, because light is part of the electromagnetic spectrum and can travel through space, whereas sound would need something for it to travel through. When we're talking about this, it acts as a particle because it can be blocked. So think about a shadow. If you put your hand in front of a light, you can't see the light. However, some of the waves can get through, and we'll talk about that later. The speed of light in a vacuum is always going to be 3 times 10 to the 8th meters per second. And so when we're talking about our equations, that's the number that we'll use for the speed there. When we talk about light, it will be only a small part of the electromagnetic spectrum. We'll talk about the other parts of it in a little bit. It ranges from about 400 to 700 nanometers in wavelength, and we have to remember that nano is times 10 to the negative 9th. So if you're putting it in a calculator, you would say 400 times 10 to the negative 9th all the way to 700 times 10 to the negative 9th. If you think about back to elementary school and you talked about the colors of the rainbow, you had Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And red has the longest wavelength, and violet has the shortest. And so this is what we see. It's the way that light breaks up, but then it also is a part of a much larger spectrum of what we see for the electromagnetic spectrum. This is the larger electromagnetic spectrum. Radio waves are the longest, and then microwaves, infrared, and then the visible spectrum is a teeny tiny amount in the middle, and then ultraviolet, X-ray, and gamma ray. The longer the wave is, the lower energy that goes along with it. So radio waves are really long and they can travel a long distance, but they don't have a really high energy with them. And microwaves then continue to get higher all the way to gamma rays. Gamma rays have a really high energy with them, but their wavelength is teeny tiny. Radio waves are what we use to transfer information from one place to another. If you're listening to a radio, it has gotten to you by radio waves. Cell phones communicate by radio waves as well. Microwaves are a smaller wave than radio waves. They're centimeters long or somewhere in there. A microwave oven utilizes microwaves to heat up your food. Water resonates at the wavelengths that are found for a microwave, and so it sends microwaves into your food. It causes your water to resonate and get all wound up and start moving, and that heats up your food. Infrared, they get smaller, and you can see that when you scan something out at the grocery store. If you use a bar scanner, that's actually going to be an infrared light. There is some red light to it so you can see where you're aiming it, but then outside of that spectrum you can use the infrared and you can scan that. Visible light we talked about is in that range of 400 to 700 nanometers. And then outside of that, getting shorter, is ultraviolet. The sun sends a lot of visible rays, but then also some ultraviolet rays. Those are the ones that cause your skin to tan or to burn. And those are the ones that you want to block and not have on your skin, causing like skin cancer and stuff. You can do that with sunscreen. Clothes will block it out usually. Glass actually will as well. X-rays then get to a higher level. X-rays can go through soft tissue, but they are blocked by the bone. And so when you see an X-ray, you're actually taking a picture of a shadow of your bone to see what's going on there. And then gamma rays have the highest energy. This is the radiation that you get from nuclear physics. It's also, if someone's going through cancer radiation, it's usually going to be either at the high end of X-rays or at gamma rays, and that's targeted specifically to go in and to break up a cancerous spot within somebody's body. So gamma rays have a really, really high energy. They can be used in a helpful way, in ways of, treating different cancers, but then can also be harmful if just unleashed. Because these are waves, we can still use the equation of V equals F lambda, where V is the velocity, F is the frequency, and lambda is the wavelength. And again, the velocity here for our electromagnetic waves is 3 times 10 to the 8th meters per second. We usually clarify that's in a vacuum, but traveling through air, that's usually going to be the same thing. It's close enough that it's not going to be enough different. The other thing that happens with this, if you look at the velocity of light here of 3 times 10 to the 8th compared to that of sound, which was about 340 meters per second, this is why you have a gap between when you see lightning and when you hear the thunder. Because you see it so quickly because it's traveling at 300 million meters per second, but then you hear it because it's only traveling at 340 meters per second. So there's a significant gap between what you see and what you hear. So let's do an example here. If we have the speed of light at 3 times 10 to the 8th meters per second, and let's say we have 400 nanometers for our wavelength here. This means that we're dealing with a purplish light and kind of at the shortest end of the wavelength spectrum for what's visible. And we want to find the frequency, and we know that V equals F lambda. And so one of the things that we have to make sure that we do is we have to take our 400 nanometers and we have to get that into meters. And nano is times 10 to the negative 9th. So we would say 400 times 10 to the negative 9th. I know that's not completely proper in the way of writing a scientific notation, but it's functional and it helps it because nano is times 10 to the negative 9th. So when we talk about our wavelength, we'll say that it's 400 times 10 to the negative 9th meters here. We're solving for F, and so we can use V equals F lambda. If we're solving for F, we'll divide both sides by lambda here. And so we'll end up with our frequency is equal to V over lambda. And we take the velocity that we have. We have 3 times 10 to the 8th meters per second. And then divide by the lambda that we have. We have 400 times 10 to the negative 9th meters. And when we do that, we end up with 7.5 times 10 to the 14th hertz. And so that's a huge frequency there. 7.5 times 10 to the 14th is that's a big number. And so that's what we're looking at for the frequency of light when we're talking about a purple light, which is about 400 nanometers. If you were to take and be solving for lambda instead, you'd still be starting with V equals F lambda. And again, your V would be 3 times 10 to the 8th meters per second. And if you're solving for lambda here, you would just divide both sides by F. And lambda would equal V over F. So you end up with kind of 3 equations. Still your V equals F lambda. Your frequency equals V over lambda, and your lambda equals V over frequency. And as we've done before, some people like the triangle method. And so in this situation, we put the velocity up here, F here, and lambda here. And if you're solving for one of them, if you're solving for lambda, you would cover it up, and it would be V divided by F. If you're solving for F, cover it up, V divided by lambda.
A photon was getting on an airplane. They asked him if he had any luggage. No, I'm traveling light.